So the differential rate law told us how the reaction rate depends on the concentrations of the reactants. Now we're going to look at a different type of rate law called the integrated rate law. And this tells us how the concentration of a particular reactant changes as a function of time. So since we can only write the integrated rate law for one reactant at a time, the easiest type of reaction to write the integrated rate law for is just one where there is one reactant. Say we have a reactant A which produces some products. And so the integrated rate law has a different form depending on the order of this reactant. So in this video, we're going to go over the equations for a 0, first, and second order reactant. So the first order integrated rate law is the ln of the concentration of the reactant equals negative kT, where k is the rate constant and t is time in seconds, plus the ln of the initial concentration of the reactant. Now this little 0 here means initial. So if you compare this equation to the equation of a line, y equals mx plus b, you can see that this can be turned into a linear equation, where y is the ln of the concentration, and then m, the slope, is negative k, x is t, and b, the y-intercept, is ln of the initial concentration. So if we make a graph of ln of the concentration on the y-axis and time on the x-axis of a first order reaction, it will be a straight line where the slope is equal to negative k. And we can also find the equation for the half-life of a first order reaction. So the half-life of a reactant is just the time it takes for the concentration of the reactant to decrease by half. So looking at this integrated rate law, we see that after a time equal to the half-life, which we indicate by t subscript 1/2, the concentration has become 1/2 of the initial concentration. So if we replace the concentration of the reactant in the integrated rate law with 1/2 of the initial concentration and solve for t 1/2, we get that the half-life is equal to ln of 2 over k. So this is the half-life in a first order reaction. So notice how the half-life does not change, because ln of 2 is a constant and k is also a constant. So for a first order reactant, each half-life is the same amount of time. Now next we have the second order integrated rate law, which is 1 over the concentration equals kT plus 1 over the initial concentration. So again, comparing this to y equals mx plus b, we see that if we make a graph of 1 over the concentration on the y-axis and time on the x-axis, then we'll get a straight line with a slope equal to k. And using the same method, we can come up with the half-life formula for the second order reaction. So the half-life is equal to 1 over k times the initial concentration. And so notice how the half-life of a second order reaction depends on the initial amount of reactant we have. So this means each half-life is going to be longer than the last half-life. Because the initial concentration is getting smaller. So say we start with 100 molar of the reactant. To find the first half-life, we're going to plug in 100 to this equation. And then so after one half-life, it has decreased to 50 molarity. And so to find the second half-life, we're going to plug in 50 to this equation. So this initial concentration in the half-life formula is not like only the very, very beginning concentration. It decreases after each half-life. And then last we have the zero order integrated rate law, which is the concentration equals negative kT plus the initial concentration. And so, a zero order reaction is where the rate is constant and it does not depend on the reactant's concentration. Because if you can imagine in the differential rate law, if the concentration of the reactant is raised to the zero power, that's just going to be 1. So here, if we graph the concentration versus time, then we get a straight line with a slope equal to negative k. And the half-life for a zero order reaction is the initial concentration over 2k. So for a zero order reactant, the successive half-lives are going to keep getting smaller and smaller, compared to a second order where they get longer and longer. And that's because the initial concentration is on the top this time, and that's going to be getting smaller and smaller with each half-life. So any questions regarding integrated rate laws are either just going to be plugging numbers into one of these formulas, or it might be asking you about a graph. So remember that we can determine what kind of order a reaction is by looking at the graphs, and so we plot time on the x-axis and either ln of the concentration 1 over the concentration or the concentration on the y-axis. And whichever one's a straight line, that tells us what order the reaction is. Remember that if the straight line has ln of the concentration on the y-axis, then it's first order. If the y-axis is 1 over the concentration, then it's second order. And if the y-axis is just concentration, then it's going to be zero order. And also remember that only in a first order reaction is the half-life constant.